We are continuing on with Chapter 8, Gases and Chem 140. Uh, we had been doing quite a few problems with the ideal gas equation, and then we get to this equation, which says the molar mass gas equation is used often to determine the molar mass of a gas whose density has been measured experimentally. We used to do a neat lab with this. I don't know if they're still doing it or not, but um, it was you would put a little bit of liquid into a Erlenmeyer flask, and you would heat it up so that it would become a gas, and it would push all the other gases out of the flask, and then you would um, put a stopper on it, let it condense back, and then you could determine what the density is. But I think what throws students on this problem a little bit, or this looking at something like this, is that let's just look at it this way. So molar mass, which is the capital M, is equal to grams per mole. All right, we've done that over and over in this class. And so D stands for density, which is equal to mass divided by volume. So then we have PV equals nRT, PV equals nRT, and so what would happen if we're trying to solve for this, and we were trying to see what the equation is that gets us to this point here. So okay, so let's solve for volume on this equation. So we get V equals nRT, and let's just go and do that, RT over P, and divide by N here. Okay, so now what we have is volume, which would be in liters, and we would have number of moles here. And then you go, okay, I'm trying to get to molar mass, which is grams per mole. So what if I multiply both sides by density, which is mass divided by volume? So mass divided by volume here, and mass divided by volume here. So that volume and that volume would cancel out. Mass divided by number of moles, oh, we got molar mass here. So this becomes the molar mass. And then instead of saying mass divided by moles on this side, well, we know that that's what density is equal to. So this becomes density, which is that D right there. So that's how we derive the equation. You don't have to derive it. You can just memorize it. Molar mass is equal to the density times the gas constant times the temperature divided by P, the pressure. All right, but if you want to look at that and kind of figure out how we got from, I think it is important. If you are planning to take Chem 170, look at how you go from here to here and mathematically figure it out using these two bits of knowledge, because it's important. It's important that you can derive one equation from another. All right, so the gas equation method, here it is. To determine the molar mass of a liquid, we weigh an empty flask fitted with a foil cap with a tiny hole for air and vapor to escape. We then put a small amount volume of liquid into the flask. We heat it up, and all the liquid in the flask vaporizes. The vapor displaces the air that was in the flask, and then we can stopper that, put just seal it off with aluminum foil, and then we can reweigh it, and the difference in the initial and final masses is the mass of the vapor, and knowing the temperature of the boiling water, the pressure in the room, and the volume of the flask, we can determine the molar mass of the liquid. It's a really cool experiment. I don't know if we're doing it in Chem 140, but it's more of a, I don't remember doing it in Chem 140. I think it's more of a Chem 175 lab. It's a neat lab though. All right, so they show us a problem similar to this. It says carbon dioxide is an effective fire extinguisher, partly because its density is greater than that of air. So because carbon dioxide has a greater density than air, it displaces the air, and the CO2 goes over the fire, and you got to have oxygen to support combustion, so it deprives the flames of the oxygen, and so we call it smothering the flame, right? So it says calculate the density of CO2 at room temperature, 25 degrees Celsius and 1 atmosphere pressure. All right. So let's write down what we have here. We have they want us to calculate the density. We know what the temperature is, 25 degrees Celsius plus 273.15 equals 298.15 Kelvin. We know the pressure is equal to 1 atmosphere. And what else do we need? We know R is 0.0821 liter atmospheres mole Kelvin. And the other thing we know is we know what the molar mass of CO2 is. So you got carbon at 12, 2 oxygens at 16 each. So we're dealing with 44.01 grams per mole. All right. So when we think about the equation, you start seeing this. It's not PV equals nRT because we don't see N here. And so we know that molar mass is equal to density times R times T over P. Okay, so we got all of these. We have we just need to solve for density, right? We know what the molar mass is. We know R, we know T, we know P. We're solving for D. So then D equals the molar mass times P divided by RT. All right. So that's how it works. That's how you solve these problems. Do I expect to do as fast as I'm doing here? No. This is a presentation. It is going to take you a little bit of time, but through doing your homework and the problems in the back of the chapter, you do develop some proficiency. All right, so there it is. Density equals pressure times the molar mass divided by RT. We know we set this up right because watch, that atmosphere and that atmosphere cancel out. Kelvin cancel out. This mole and this mole cancel out, and you're left with grams in the numerator and liters in the denominator, which is the density for gases. Generally, gases are measured in grams per liter, and we get 1.8 grams per liter for the answer here. It's a good problem. I like it. Make sure you can do this problem because it's a neat problem that we can determine the density of an unknown gas. Or of a known gas, I guess we should say, a known gas, based off its molar mass. All right, so the next slides are all about the laws that created the ideal gas equation. So Boyle's law is first. Boyle was an Englishman, and he saw the relationship was inverse between volume and pressure. So what he's saying here is that as the volume goes down, then the pressure goes up. That's an inverse relationship. So you guys know this. If you take a container and you have a piston here and you decrease the volume to down here, and all that gas that was up here is now all trapped down here, that the pressure is going to go up. So it's an inverse relationship. So volume is this is a proportional sign. So you could say volume is proportional to 1 over P, but mostly what people say is volume is inversely proportional to pressure. Volume is inversely proportional to pressure. So he did these experiments. If you look at this next slide, this is how he could tell something was going on. So he took a J tube, a glass tube that's sealed off at the end here. He fills it completely full. He fills it tips it over so that this is completely filled with, well, it's a J tube, and he pours mercury in here, so it traps this gas here. It traps the air here between here and here. And so this is what it looks like. You have this level of mercury, and he has about 100 milliliters of gas trapped inside of this J tube. It is sealed off at this end here. So then, if he increases the amount of mercury in the tube, 760 millimeters, which is an atmosphere of mercury, he notices that the volume is decreased by half. And if he adds double that, 2 atmospheres, he knows that it decreases to 33 millimeters of volume for the gas here, the air. So he can see experimentally that, yeah, if he doubled it, then it's 50, and then if he doubles it, no, it's not quite half of 50, right? It's 33 milliliters. So, but he could plot that difference. He could plot that difference on a piece of graph paper, and this is what he would get. All right, and notice it isn't a linear relationship. It is it's bowed here because it gets harder to compress the gases together as they get closer together. But if you plot volume versus 1 over pressure instead of just pressure, you get a nice linear line, which shows that as the pressure decreases, or 1 over the pressure gets smaller. So this means that's getting larger. 1 over the pressure, this gets smaller. That the volume goes up. So as here you can see it easily, as the pressure decreases, or as the pressure increases, the volume decreases. All right. And here, as the if you want to get a larger number down here, then this has to get smaller here, and so therefore you get a nice positive linear line there. All right, so the type of problem you're going to have here, especially if you like scuba diving or snorkeling, says a skin diver takes a breath at the surface. He fills his lungs. So here's what we have. Volume 1 is equal to 5.82 liters. And then he dives to, and we're going to assume the pressure initially is 1 atmosphere, right? And then he dives to a depth where we don't know what the volume is, but we know that the pressure now is 1.92 atmospheres, which would be about probably around 30 feet underwater. And so you can tell this is not an ideal gas equation. We don't have N, we don't have T. We assume the temperature is not changing. We assume the temperature is constant, and the pressure at the surface is exactly 1 atmosphere. So when you see a problem like this, then you're going to say, oh, this is a Boyle's law problem. So this is P1 times V1 equals P2 times V2. You need to memorize that equation. Memorize this equation, Boyle's equation. And what we're solving for is V2, so V2 equals P1 times V1 over P2. So, you know you set this up right. When you plug in your answers, you can see the 2 pressures cancel out. You're left with units of liters, which is a volume unit. And you can see that the lungs have decreased in size from 5.82 liters to 3.03 liters due to the pressure applied to the body, due to the atmospheric pressure plus the pressure of the water above the skin diver. All right. So this is the problem. When you go down further and further into the water, the pressure gets greater and your volume gets smaller. If you shoot up to the surface really quickly, you can either get the bends where the nitrogen that's from the air dissolved in your bloodstream comes out as bubbles, and they usually go to the joints and cause you to draw up. Or the worst case scenario is you get an air bubble or gas bubbles pop in your, it could be nitrogen or oxygen, whatever, but they pop in your lungs and you get an embolism and it kills you. So, that's the whole thing about scuba diving. You never just shoot up to the surface. Even in you have to control the panic if something's happening, but you have to go up as you go up, you have to go at a certain rate, and you should be blowing bubbles out of your mouth. Although it seems strange, like if you're out of air, as you go up, you blow a steady stream of bubbles out of your mouth so that you don't pop your lung and get an embolism. All right, so the next law, so Boyle's was about pressure and volume relationship. Charles's law is a direct relationship. Volume is directly proportional to temperature. So you guys know this. If you take a balloon and you put it in a hot car, it's going to expand. Now, the number of moles is the same, but at higher temperature, the molecules are moving faster and they're pushing outward on the surface of the balloon, and it causes the balloon to expand. So the higher the temperature, the greater the volume that exists, that the gas has to exist in, if you want to keep the pressure the same. Which brings me to this: the pressure in both of these balloons, the atmospheric pressure would be 1 atmosphere. So to keep the pressure 1 atmosphere inside this balloon with the higher temperature, it has to be able to expand. If it doesn't, then the pressure would build up inside the balloon. But just remember, the pressure inside the balloon and outside the balloon has to be the same. Otherwise, if the pressure inside the balloon is greater, the balloon's going to keep expanding, and if the pressure inside the balloon is less than atmospheric pressure, it's going to contract. So his equation, when he compares at two different systems, like volume 1 T1 and volume 2 T2, his equation becomes V1 over T1 equals V2 over T2. So you need to memorize that equation. That is Charles's law equation. Okay, so let's look at a problem. Do they show us a problem, or do I skip over it? They just show you, they show you what it looks like. So here you have a balloon. It's got a fixed number of moles of gas in it. And I pour liquid nitrogen, which is really cold, onto the balloon, and you see the balloon collapse. Because the molecules inside the balloon aren't moving as fast, they don't require as much volume, and you see the volume actually decrease. So it says the pressure inside the balloon, which is roughly equal to the external pressure, remains constant in this process. And you can see as the temperature lowers, the volume decreases dramatically. All right, so this one's kind of showing the molecular level, what's going on with Charles's law. This piston represents atmospheric pressure. And as you increase the temperature, these molecules have more kinetic energy. They're moving around, and if you want to keep the pressure the same, then the volume has to get larger. If you want to keep the pressure the same, notice the pressure is not changing in any one of these. And this is the way we represent atmospheric pressure. This piston here represents atmospheric pressure. So if we want to keep the pressure the same, then the volume has to get larger. If we don't, if we leave it like this and we increase the temperature, then these things are striking the container more. The molecules are striking the container more, and the pressure is going to go up tremendously. So if we want to keep the pressure the same, then the volume has to change. So let's look at a problem here. It says you've got a sample of argon that has an initial volume of 14.6 liters. And it's at a temperature of, we'll just go on and say 298 Kelvin. That's what 25 degrees Celsius is. And they want to know what the new volume is when the temperature is equal to 50 plus 273 is 323. So you know this is an ideal gas flow. You don't have anything about N. You don't have anything about well, that's the big one. And you've got two different volumes and two different temperatures. And so it's not a combined gas law, because the combined would be P1 V1 over T1 equals P2 V2 over T2. You don't have as much information as a combined gas law problem. So what you have to memorize is Boyle's equation, which I talked about. You're solving for V2, so you got to multiply both sides of the equation by T2 to keep the equality in force. That cancels out with that. And you get, if we clean this up, it's V2 equals V1 over T1 times T2. All right, so next slide. So there we have it. We have V1 over T1, and then there's the multiplied by T2. You know you set this up right because the Kelvin cancel out, and you're left with units of liters, which is the unit for volume. And here's another thing you got to be thinking. If the temperature goes from 298 to 323, you better make sure the volume increases. So it goes from 14.6 to 15.8. If your volume decreases here after you raise the temperature, and you know there's a direct relationship between volume and temperature, that's a red flag to say, hey, I've done something wrong. I've got something flipped, probably. So just make sure you kind of think about the problem. Yes, if you increase the temperature, the volume better increase. And if it doesn't, you've made a mistake, even though the unit's canceled out maybe. All right, next relationship's much like Charles's law. It's a direct proportion between volume and number of moles. As the volume goes up, the number of moles has to go up. Or let's do it this way. The number of moles go up, the volume has to go up if you want to keep the temperature and pressure the same. So once you have a container, if you add more moles of gas, then the volume has got to expand to accommodate these extra molecules if you want to keep the pressure the same. So that equation looks just like, kind of like Boyle's equation. Charles's equation. V1 over N1 equals V2 over N2. Okay. So in Avogadro's law, the volume of gas at constant temperature and pressure is proportional to the number of moles. So you can see here they got 5 molecules here, which represent 5 moles. They open the valve, you add more molecules. Now you're trying to keep the pressure constant, right? Pressure is constant. So the volume has to expand to keep the pressure the constant. So as we add more molecules of gas, we have to expand the volume to keep the pressure the constant. Otherwise, if we keep the volume the same, the more moles of gas in here, the more it's striking the surface of the container, and the pressure is going to go through the roof. So what does a problem look like? You've got N1, you got 1.50 moles of gas, occupies a volume of 10.0 liters. We know that N2, we've increased the number of moles to 3.0 moles. And they would like to know what the volume of gas is, assuming ideal conditions, ideal gas, and that the pressure doesn't change. The pressure is constant. So, you can do it N1. Either way you want, either way you want to do this here. You could say V1 over N1 equals V2 over N2. And that you can say, why do you want to do it that way? Because it's easy to solve then for V2. I multiply both sides by N2. That cancels out. I'm solving for V2. So V2 equals N2 times V1 over N1. That will give me my answer. And that's what we have right here. So you got N1 V1 times N2. And look what happened here. You doubled the number of moles, kept the pressure constant, you doubled the volume. That's what's kind of cool about that. mean, you really don't even have to do the equation, right? If you double the number of moles and the pressure has to be constant, you have to double the volume. And again, assuming temperature remains constant as well. All right, so this is the last section, this Dalton's partial pressures. This is really important. It's really easy. You guys probably could even figure this out. You have a container. So here's my container. And I have gas A in here. And so gas A is going to register on my pressure gauge here. Okay? And so what happens is assuming the volume is held constant and the temperature is held constant, then so here's the pressure of gas A, all right? And here's the number of moles of gas A. If I put in another gas B, I want to see the pressure go up, because we saw with, with Avogadro's law, if you increase the number of moles, you increase the volume, direct proportion. Well, here, as we increase the number of moles of gas, we're going to see the pressure go up. So we got the pressure of B now. Then I put in another gas C. Maybe I put in more gas C than A or B. So now I see the pressure go up like this. All right, now the pressure I'm reading here is the total pressure. But the total pressure is equal to the pressure contributed by gas A, or let's make it a capital A, the pressure of gas B plus the pressure of gas C. That's Dalton's law, that the total pressure of inside a container is equal to the sum of the individual pressures, which we have a name for that. We call them partial pressures. So this is the partial pressure of A, this is the partial pressure of B, this is the partial pressure of C. When we sum up the partial pressures, we get the total pressure inside the container. That's what Dalton's law says. Makes sense? You can see it makes sense because as you add more gases, it's striking the diaphragm of the pressure gauge more, and we're going to register an increase in pressure here. So here's what it looks like. They did a nicer picture than me. So notice the volume is not changing. It's exactly the same in all three. The volume is not changing. The pressure is changing. So we got gas A here. We got gas B here. And we can see what the pressures are here. If I add gas A to gas B, now I have a mixture of gas A and B, and the total pressure is equal to the pressure of A plus B. And that's what we see. If we add these two things together, we get that pressure there. So Dalton's law, each component of the gas mixture exerts a pressure independent of the other components because these gases are not attracted to one another. They are moving in linear paths until they strike another molecule or the wall. The collision is elastic. It means all the energy stays with the gas after the collision. And so that's why we're able to say we can add gas A to gas B and the pressures are additive. So here's a classic example. It says you got a 1 liter container. So I draw a picture like this and say, here's my 1 liter container. And I've got 0.215 moles of nitrogen gas in here. And I've got 0.0118 moles of hydrogen gas. And the temperature is constant at 25 degrees Celsius. Determine the partial pressure of each component and the total pressure. All right, so you're looking at this and going, well, they don't give us pressures. And this is what I know. The total pressure is going to equal the pressure of the nitrogen gas plus the pressure of the hydrogen gas. So I got to solve for these two things to get this. So how am I going to find out what the pressure of the hydrogen gas is? Well, the pressure of the hydrogen gas equals, N, the number of moles of gas I have. So we're going to think PV equals nRT, right? PV equals nRT. We're going to solve for P. So the pressure of the hydrogen gas equals the volume, which is 1.00. Well, let's do this. The pressure of the hydrogen gas equals the number of moles of gas we have, which is 0.0118 moles of hydrogen gas, times R, 0.0821 liter atmospheres mole Kelvin, times the temperature. All right, so let's do the temperature, which is 298 Kelvin. Running out of room there. And then divide by the pressure, which is, or divide by the volume, which is 1 liter, 0.100 liters. Yeah. All right, so let's make sure we did this right. That mole and that mole cancel out. That Kelvin cancel out. That liter and that liter cancel out. I'm left with the atmospheres, which is what I'm looking for. Do the same thing for the nitrogen, and I'm just going to flip to the next slide to show you that. Oops, they don't actually, did they do it? Yeah, there we go. So here it is. There's N, there's R, there's T divided by V. There's what we just did. Do the same thing for nitrogen. The moles of nitrogen are 0.215. Notice this, and this are all the same. And there we have 5.26 atmospheres of nitrogen. If we add these two together, the total equals the total pressure. So the pressures individually we're asked to find, and then the total pressure we're asked to find. These are easy problems. As long as you remember, you're probably going to be working with PV equals nRT. And the other thing I think it's really important is you draw a picture of it. Draw a box. There's your volume of your container. Tell me what gases are inside there, what moles of each gas are inside there to help you solve the problem. Not a bad problem, just requires you to think in steps. All right, mole fraction. So what is a fraction? A fraction is an amount out of the total. All right. So a mole fraction, which is given by this symbol, is the number of moles of an individual substance divided by the total number of moles. We can also think of a mole fraction as the individual pressure of a gas divided by the total pressure of the gases. And you go, how did you do that? Well, think about PV equals nRT, and N is equal to PV divided by RT. What if all that's held constant? The temperature is held constant, R is a constant. What if the pressure, if the volume is held constant, then N is related to P by N is equal to P times V over RT. Or if you don't like that, if you like pressure is equal to N times RT over V. But so that's the relationship between mole fraction. You can think of it in terms of number of moles, but you can also think of it in terms of number of the pressure of the gases. So things to remember is a mole fraction always, when you add up, so the pressure of any individual component is always less than 1. When you add up all the components, all the mole fractions, like mole fraction of hydrogen gas plus the mole fraction of the nitrogen gas, it always has to equal 1. That's the maximum value you can have when you sum up the mole fractions. And mole fractions are dimensionless because this is in moles, this is in moles. It divides out. This is in atmospheres, this is in atmospheres. They divide out, so mole fractions are dimensionless. All right, so let's look at a problem. It says 1999, the FDA approved the use of nitric oxide to treat and prevent lung disease, which occurs commonly in premature infants. The nitric oxide used in this therapy is supplied in a nitric oxide mixture. Calculate the mole fraction of nitric oxide. All right, so let's draw a picture. You've got a 10-liter container. So that's the total volume. They tell you that's at 25 degrees Celsius, which we're going to convert to 298 Kelvin. And it contains 6.022 moles of nitrogen. And it contains the total pressure inside the container. The total pressure is equal to 14.75 atmospheres. Okay. So, how are you going to solve this problem? And there are multiple ways to solve this problem. So, what I would recommend that you do here is you stop the video and you try to work this out on your own, and then start the video and see did you make a good decision or not. Okay, so try that out and see if you can do this. All right, welcome back. So the first thing you did is convert the 298. All right. So here's what it says. Using the ideal gas equation, the total number of moles in the cylinder, subtract the moles of N2 from the total, determines the moles of nitric oxide. So like I said, there's more than one way to do the problem. And so let's talk about the way they did it. So the total number of moles of gas is equal to the pressure total, which was given in the problem, 14.75, times the volume of the cylinder, which is 10 liters, divided by R, and the temperature is 298 Kelvin, which was 225 degrees Celsius. So this is the total number of moles of gas inside the cylinder. Now, if you subtract the total moles by the moles of nitrogen gas in the cylinder, you find that you only have 0.007 moles of nitric oxide. The mole fraction of the nitric oxide is 0.007 divided by the total, and that would give you the mole fraction of the nitric oxide. All right, so let's go back. Go back to the original so we can follow what's going along here. That's why you got to draw a picture here. You know the total volume, you know the temperature, you know the total pressure. And so PV equals nRT. And N equals PV over RT. And you start looking at it. There's the total volume, there's the total pressure, R, and there's the temperature. And you solve for N, which is the total. You subtract off the N of the nitrogen. That gives you the N of the nitric oxide. Good problem, a little harder. That's probably about the hardest problem we've done in this chapter, but I think you can handle it. The main thing to me is draw the picture and write down your information. So we are progressing. Before, we just read the problem, we wrote down our information given in the problem, and then from that we were able to derive which equation we need. Here it's really good to draw a picture because you're still pulling out the information from the problem, but then you got to start thinking, well, I know that I can figure out the total number of moles if I've got the pressure and the volume and the temperature. And then I've got the moles of nitrogen, so if I subtract off the moles of nitrogen, I'll get the moles of nitric oxide. All right, last step. You might have done this in the lab, you might not have, but here what they're doing, they're generating some gas, and you've got usually we use a graduated cylinder, but there is a gas thing called a gas tube. You fill it completely full of water. You pull the bottom off of it, and it completely all the water is in here. And then as the gas is generated here, it bubbles up through here and it pushes the water out. It's called water displacement. So if I push all of the water out of the tube, then what I know is I know exactly what volume of gas I have here. I know that the total pressure inside the tube is the same as atmospheric pressure. And so the only thing that's tricky about this is the pressure of the water. Water actually has a vapor pressure that actually adds to the pressure inside the container here. So the total pressure inside the tube is equal to the pressure of the gas plus the pressure of the water. Now, when we do this in lab, most of the time, we just say this is negligible, and we have you calculate it just based on this part here. But technically, you're supposed to add in the pressure of the water. So I believe if you've done a lab on this, they just said forget the water, but the water is part of it. So let me show you how this works. So if the water temperature is 25 degrees Celsius, this is what the pressure is that's contributed by the water vapor inside that gas cylinder, inside the cylinder. So we're going to have to add that on. So that's what we have to do. So the total pressure, again, is the pressure of the gas, which is fine, but you also got to add the pressure of the water vapor that's in there as well. All right, so here we go. When calcium metal is placed in water, hydrogen gas is produced. Determine the mass of the hydrogen produced. So we want to know the mass of the hydrogen produced when the temperature is 25 degrees Celsius and the pressure is 0.967 atmospheres. Okay. And when 500 and then the volume of gas collected is 525 milliliters. Okay, so you ought to be thinking, okay, what's the pressure of the hydrogen gas? Okay, because what you're trying to do is you got the total pressure is equal to the pressure of the hydrogen gas plus the pressure of the water. Well, and we're trying to get the mass of the hydrogen gas. So the total pressure, we can convert that to, so what we know is if we had the total pressure and we subtract off of it the pressure of the water, that will give us the pressure of the hydrogen gas. So the total pressure is 0.967 atmospheres. All right. And we subtract off of the pressure due to the water, and you go, how am I supposed to know that? Well, you know, and I don't expect you to memorize this, you know from looking at the table that we just saw, at 25 degrees Celsius, it's 23.8 torr. All right, 23.8 torr. So here's what we know. 23.8 torr and 760 torr equals 1 atmosphere. So multiply that out on your calculator. Let's see what that equals. 23.8 torr divided by 760 equals 0.0313 atmospheres. So we got to subtract off 0.0313. And that's why they probably don't have you do it in the lab. There's probably enough error that if you're not doing this precisely, that's negligible compared to that amount. I mean, let's do that. Let's take 0.03 divided by 0.967 and then multiply by 100. And this is 3% error. 3% error if you don't throw that in there. So, all right. So let's look at the problem. So that's where they calculated it, right? And then once we get the number of moles, we can use the molar mass to convert them back to grams of hydrogen. So here we go. So the first thing is we took the total pressure, subtracted off the pressure due to the water. This is now the pressure of the atmosphere of the hydrogen. We know that PV equals nRT. If we solve for n equals PV over RT. This is what we did here. We know we set this up right. If you write this stuff out, you won't make these mistakes. And you can see everything cancels out except the moles, which is in the quotient of a quotient. So that's how many moles of hydrogen gas you have. You know, at this point, anytime you multiply moles times molar mass, which is what that is, of the hydrogen. Now we're talking diatomic hydrogen. Then, and I'll put capital M for molar mass, that'll give us the grams of hydrogen. So, I think what makes these problems a little harder is they're not just one step. We started out at the beginning of this chapter, just a one-step problem, convert from atmospheres or millimeters of mercury into atmospheres. Now you're getting into problems that take 3 or 4 steps, and you've got to do enough problems to see the pattern and to record the information and think about how you're going to manipulate it to get the answer. So how do you get good at this? It's practice. It's doing the homework. It's doing the odd problems in the back of chapter 5. It is a short chapter. It's not as big as some of the other chapters we've done. But you got to see the pattern of how you solve these problems. If you'll do that, you'll do fine in chapter 5. Most people do well in chapter 5 if they follow these procedures I've talked about. And it generally pulls your grade up a little bit. But you have to watch the units, and you have to think about which equation I need to apply to get to the correct answer. And for these last couple here, you really need to draw a picture and think about it. All right, I hope that helps, and that finishes chapter 5.